All right, welcome back to College Algebra. Today we have section 3.6, the fundamental theorem of algebra. Basically, I'm going to kind of wave my hands at a few theorems here just a little bit, and because, yeah, the proof of them is really beyond the extent of this course. So let's start with the fundamental theorem of algebra. All it says is that if you have a polynomial with complex coefficients, so you could even have i's as coefficients for your polynomial, the polynomial is guaranteed to have at least one complex zero. Now this is going to be useful for us because the fundamental theorem doesn't preclude having a polynomial that just has real number coefficients. Complex number, every real number is also a complex number. So basically this gets us at least one zero for every polynomial. And as we'll see here in just a second, it's going to get us a lot more than that. That brings us to the linear factor theorem. Basically, the linear factor theorem says that any polynomial can be split up into the product of its linear factors. So I have an x minus c1 here all the way down to x minus cn. Those are just the zeros of our function. Okay, so the c's here are just my zeros. The a sub n would be the leading coefficient of my polynomial. And so if you find all the zeros and then you just put the leading coefficient in front, it will be equal, guaranteed. And it turns out that that actually flows pretty nicely out of the fundamental theorem of algebra. But again, I'm just going to kind of wave my hands at this a little bit right now. So the real reason that we want the fundamental theorem of algebra in this course is because since it then gets us the linear factor theorem, it will then also get us to the number of zeros theorem. And all that says, end of the story, is that any polynomial will have as many zeros as its highest degree. So if you have a fifth degree polynomial, you are guaranteed 5 zeros. However, there's nothing that says that they have to be very nice. Okay, they could be complex numbers, actual complex numbers with I in them. Okay, so they're not guaranteed to be nice things like 2 or 5 or negative 3. You could get, I don't know, 7 plus 2i. All right, so that's a real possibility. So we're going to look at an example here of a polynomial that has, it's going to have 3 zeros, and 2 of them will actually be complex zeros, and we'll look at what happens with that. And then we'll do some other stuff here as we go through the section. So hang on, let me change the board. All right, so now I have an example. I have a polynomial that I want to find the zeros for, and I actually have, so you can start looking at that. Again, feel free to pause this at any time. That would be a great way to, if I happen to be going too fast. So my polynomial is x cubed minus 3x squared plus 7x minus 5. So I just wanted to jump right in. I didn't go through Descartes' rule of signs on this one, though you should be able to do that. I did start with my rational zeros. I know that the divisors for p, for the 5 at the end, are 1 and 5, so plus or minus 1, plus or minus 5. And for q, it's just a 1, which is super nice. So we get plus or minus 1 there. And the fractions that we can make out of that are just positive and negative 1, positive and negative 5. 4 choices. So at this point, I threw it in my calculator. Okay, you'll see I have synthetic division up here next, but I threw it in my calculator because remember, what I'm going to do is I'm going to compare this list with what I see on my calculator. And what I'm really hoping is to find at least 1 zero that way, because if I can do that, I can take this from a 3rd degree down to a 2nd degree. So it turns out I can. If I try 1, looks like it works on my calculator, looks like it works here. If I try 1, as you can see, I did the synthetic division, I got 0 at the end. That means that 1 is a 0. What that allows me to do then is to rewrite my polynomial slightly factored. So I pulled out the x minus 1, right, there's the 0 from the 1, and I'm left now with a quadratic, x squared minus 2x plus 5. I then jumped in and did the quadratic formula on this quadratic. I'm done with that x minus 1. I found that 0 already. Okay, that part is already done. X equals 1 is a solution. So I jumped in, I did the quadratic, and you can see that when I get down here, I get a square root of negative 16, which gives me a 4i. I split it up because I have 2 very nice answers that come out of that, 1 plus 2i and 1 minus 2i. So now, one more thing that I did want to show you here with this problem is we can write this polynomial in what's called its factored form. We already have one factor that we pulled out. So I'm going to write this over here. We have the x minus 1. But now we have these two pieces, and so we get x minus both of them. So minus 1 plus 2i. And I'm running out of room, so pretend I'm multiplying this x minus 1 minus 2i. We're going to put that in parentheses. This is the factored form. Importantly here, my leading coefficient is a 1. Remember, we had that linear factor theorem, so we really technically need a 1 in front, but since it's a 1, we don't usually write it. If we had something like, say, a 7 there, we would need to put a 7 in front of this. And that would be the way to make this work out. We just take x minus each of our three zeros. So there we go. We have a polynomial, had some complex solutions. We found all of the solutions, and then we wrote it out in its factored form. So there you go. I have one, sorry, before we go on, I do want to point out one more thing. You might notice that the two complex solutions we got are 1 plus 2i and 1 minus 2i. Now, if you watched my last video on section 3.5 when we did complex numbers, you'll know that those are what we call complex conjugates. And you might be thinking, well, that's kind of funny that we got complex conjugates for our two complex solutions. Well, not really. And here's why. Because we started with real number coefficients. And the only way we can have real number coefficients is if all the i's drop out. So we have this factored form. If we multiply this back out, it needs to end up without any i's in it. And the only way that happens is if we have the conjugate pair. So that's actually something called the conjugate pair theorem. You're welcome to go look it up. I'll just kind of mention it here. The conjugate pair theorem just says that anytime one complex number is a solution, so is its conjugate pair. And so that's really pretty nice. And actually, we're going to take advantage of it here in just a second. So let me get a new board. All right, so the last thing I have here is we want to try and build a polynomial. We're going to start with zeros, and we're going to build the polynomial that has those zeros. I didn't quite finish the problem. I ran out of room on my board, but I think I got it far enough so that you can finish it up. So let's see what we have. Find a polynomial with real coefficients of degree 4 with zeros of 2, -3, and 1 minus 3i. Now, importantly, I've asked for a polynomial with real coefficients. And from what we just said about conjugate pairs, we know that since 1 minus 3i is a 0, 1 plus 3i must also be a 0. So go ahead and ignore this bit down here. We'll get there in just a second. So I really have my 4 zeros. 2, -3, 1 minus 3i, and 1 plus 3i. So then what we do is we can take each of those zeros and solve them so that we have 0. What that's going to do is it's going to produce the linear factors, those little pieces in parentheses, that we can then multiply together to give us a polynomial. So I subtract 2, get x minus 2, add the 3, subtract 1 plus 2i, and subtract 1 minus 2i. So I have 4 pieces here, and you notice I brought them down. Here's my x minus 2, my x plus 3. For the 2 with the complex numbers, I distributed the minus sign. So I have x minus 1 and minus 2i, and then x minus 1 and plus 2i when I distribute that minus sign. So unfortunately, we do need to multiply this out. We want a polynomial, we want real coefficients. We certainly don't have that yet. So the part that I did for you is I multiplied the 2 complex pieces together first. I would recommend starting here. Okay? You don't want to do like x minus 2 times x plus 3 and then start multiplying it by these guys. Because if you do that, you're going to make a really big mess. By multiplying the conjugate pairs together first, the i's will go away and your life will get a lot nicer, as we'll see here in just a second. So I multiplied these two things together. I'm really careful. X times x is x squared. X times minus 1 is a minus x. X times plus 2i is plus 2ix. Then I do the minus 1. Minus 1 times x is minus x. Minus 1 times minus 1 is plus 1. And minus 1 times 2i is a minus 2i. Finally, I take the negative 2i through. Negative 2ix, plus 2i, sorry, and minus 4i squared. And now the good news is notice that all these pieces with I go away. There's a positive 2ix, there's a negative 1. Here's a negative 2I and a positive 2I. And of course, we remember that I squared is equal to negative 1. What that does for me then is it really turns that minus 4 into a plus 4. So 4 plus 1 gives me this 5. And then I have my x squared. I have a minus x and a minus x to make it minus 2x. Now I don't have any i's left. What do we still have to do? A lot more multiplying. It's not pretty, but hopefully it's something you're pretty comfortable with. We still need to multiply those three things together, but at least we don't have any more i's running around. Okay, so do yourself a favor. Start with the pieces that have the I. It'll just make life so much easier if you do it that way. So good luck. Yeah, and thanks for watching my video.